Problem set on chapter 20, current, electricity and Ohm's law. The first problem, it talks about a defibrillator that passes 12 ampere of current through a person for 0.0100 seconds. How much charge moves and how many electrons pass through the wires connected to the patient? Now, from the definition of current, we know that current is the rate of flow of charge. So I is delta Q by delta T. Rearrange that to make delta Q the subject, so it's I times delta T. And time is already in seconds. Current is in ampere, so we get 0.120 coulombs. In the B part, how many electrons pass through the wires? And for that, we have to remember that all charges are integral multiples of the electronic charge, which is given by the formula Ne is delta Q by QE. Now remember that here delta Q is the total charge, which we have already found, and then Q sub E is the charge of an electron. So that gives 7.50 times 10 to the 17 electrons. Bringing us to the next question, which talks about an open heart surgery where the defibrillator is again used and the resistance of the path is 500 ohm and a 10 milliampere current is needed. What voltage should be applied? The resistance is given and the current is given. You're asked to find the voltage. It's a simple application of Ohm's law where voltage is the product of current and resistance, and the current has to be in ampere, so that's why it's changed into 10 times 10 to the negative 3 is to change milliampere into ampere. And then you have the resistance, so you get 5 volt, and that is the answer, 5 volt. In the third question, you're to find the drift velocity of electrons for a wire made of silver, and given there is one free electron per silver atom. One free electron per silver atom, and the atomic mass of silver is given. What is missing out in this problem are two more quantities that are given. The area of cross section of the cable is given, which is 3.31 times 10 to the negative 6 meters squared. So that's given. And here we have to use the Avogadro number. Remember, the Avogadro number is the number of atoms in 1 mole. Number of atoms in 1 mole, which is 6.02 times 10 to the 23. Now the atomic mass of silver is 107.9 in grams. So the number of atoms in 1 gram mole would be 6.02 times 10 to the 23, but in 1 kilogram mole, you'll have to multiply it with 1000. So that's what I've done. So the 10 to the power 23 becomes 10 to the power 26, because 1000 grams make a kilogram. So number of atoms in 1 kilogram mole is Avogadro number multiplied by 1000. That's why the 10 to the 23 became 10 to the 6. And since there is 1 electron per atom, the number of electrons would be the same, but now we're trying to find the electron density of silver. So when we say electron density of silver, we're trying to find out the number of electrons in 1 meter cube. Because we need that quantity, the number of electrons per meter cube in 1 meter cube. So first we have to find the number of atoms in 1 meter cube, because the number of atoms is equal to the number of electrons, because 1 electron per atom. Now in order to do that, we use the number we got, the Avogadro number times 1000 divided by the atomic weight of silver, which is given, and then we multiply with the density of silver. So this number is the density of silver. Once you get the number electron density, we directly plug it into the formula I is equal to NaVdQ, where N there is the number of electrons in 1 meter cube. So that's the electron density. That's why we found it out. And since we know all the terms now, we can rearrange to find the drift velocity. And another term that was not given in this problem, which should have been given, was that the wire was carrying a current of 20 amperes. See that? 20 amperes. So that was given. And I forgot to type it out. So that 20 ampere is given in the problem. So once the current is given, we know the value of N, we know the charge of an electron, and the area is given. Plug it in and we get the drift velocity to be 3.10 times 10 to the negative 4 meter per second. Drift velocity is usually small, and so that makes sense. That's a real small velocity. The diameter of a zero gauge copper wire is 8.252 millimeter. Find the resistance of a 1.00 kilometer length of such wire used for power transmission. So in this question we have the diameter, we have the resistance. Now we have to find the resistance, and the length is given. Another quantity that would be given is the resistivity or specific resistance of copper. So that would be given. So since the diameter is given, we can find the radius, which is half of that, and that's in millimeter. So we got to change it into meter, which is either divided by 1000 or multiply with 10 to the negative 3 meters. So that's the radius. Now, since we have the radius, to find the resistance, the formula is rho L by A, where rho is the resistivity, L is the length, A is the area. Length is given in kilometers, we got to change it into meter. And then the area of cross section is pi r squared, because the cross section is circular. The area of a circle is pi r squared. So pi r square, and I think I forgot to square it, so it has to be that squared. I did the calculation properly, but I forgot to square it. So that's how we do this question. The next question, to what temperature must you raise a copper wire originally at 20 degrees Celsius to double its resistance? Does this happen in household wiring under ordinary circumstances? So this question is talking about the change in resistance with temperature. So if the initial resistance is R, then at 20 degrees Celsius, at what temperature does the resistance become 2R? Okay, so we need the formula for change in resistance with temperature, which is R is equal to R naught 1 plus alpha delta T. Okay, where R naught is the resistance at 20 degrees Celsius and R is the resistance at any unknown temperature, and which is given as 2R naught. So we substitute for R as 2R naught, and this is R naught, and then rearrange this, just do the math to get 1 is equal to alpha delta T, because I cancelled out the R naughts. And then to find delta T, just do 1 by alpha. Like I said before, this is a constant. Alpha is the temperature coefficient of resistance. That's what it's called. the temperature coefficient of resistance is how much the resistance changes for 1 degree change in temperature. So once that's given, just divide by that, you get 256 degrees Celsius. But do not forget that that is the change in temperature. But the question asks us to find the actual temperature. So since we started at 20 degrees Celsius and the temperatures must be increased by 256, the actual temperature would be 276 degrees Celsius. And for the second part, the B part, does this happen in normal household wiring? No, the temperature is that high, it would not get to that temperature, right? Number 6, find the power dissipated in each of these extension cords. An extension cord having a 0.06 ohm resistance and through which 5 ampere is flowing. In the B part, a cheaper extension cord that uses thinner wire, of course, that's why it's cheaper, and which has a resistance of 0.3 ohms, which is much greater. Okay, so you know that when the radius decreases, the resistance increases. So the second extension cord, which is cheaper, has a much higher resistance, which is going to lead to disastrous results, as I'm going to show you. So to find the power dissipated, we have to first use Ohm's law and find the voltage. So the current is 5 ampere, the resistance is 0.06 ohms. So the voltage dropped across the extension is 0.3 volt. And then the power is I times V. And so since we know the current is 5, multiply the 5 with 0.3 and you get the power wasted in the extension cord as 1.50 watts, which is okay, which is a small amount of power. Now in the second case, do the same thing. Now find the voltage, which would be much higher because it's 5 times 0.3. That gives 1.5 volt, and therefore the power dissipated will also be higher. 5 times 1.5 gives 7.5 watts. Now that's a lot of power wasted in the extension cords, and so it's very important to buy extension cords that are thicker and therefore ensuring that less power is wasted. It's also important to note that more heat is produced in a thinner cable, which could lead to a lot of heating and the insulation could come off. Here's question 7. With a 1200 watt toaster, how much electrical energy is needed to make a slice of toast? Cooking time is 1 minute. And if the cost is 9 cents per kilowatt hour, how much does this cost? All right, so the first part, we are given the power and we're given the time. Of course, time has got to be in seconds. So once you have the power and the time, you can find the energy, because energy is just the product of power and time when time is in seconds. So the power is 1200 watts, time is 1 minute, which is 60 seconds, and so it gives 7.2 times 10 to the 4 joules is the energy required, the electrical energy required. Okay. Now in the B part, you notice that it's a particular unit now. It's kilowatt times hour. That's how electrical companies measure energy. So we have to change into kilowatts and then multiply with hour. I'm going to show you. So 7.2 times 10 to the 4 joules, right, multiplied by 9 cents per kilowatt hour. Okay, so 1 kilowatt hour is 3.6 times 10 to the 6 joules. How do I get that? Remember that 1 hour is 3600 seconds. 1 hour is 3600 seconds, And then because it's a kilowatt, you have to multiply 3600 with 1000. Okay, so I think you got it. So that's why it's 3.6 times 10 to the 6, which is the same as 3600 multiplied by 1000. All right, so that's how you change it. So when you do the calculations, you get 0.18 cents. 0.18 cents. That brings us to number 8. Alkaline batteries have the advantage of putting out constant voltage until the very end. And how long will an alkaline battery rated at 1 ampere hour? Note the unit. Batteries are always rated with current multiplied by time. Let me explain what that means. This means that if 1 ampere is being drawn from the battery, it'll last for 1 hour. It's 1 ampere hour. So 1 times 1. But if a certain equipment was drawing only half an ampere from this battery, then it would last for 2 hours, because 0.5 multiplied by 2 is 1. So whenever you multiply the current drawn with the time in hours, you should get 1 for this battery. And then it continues to say this battery has a voltage of 1.58 volt, and it's used to light up a 1 watt flashlight. So how long will it last? We're asked to find the time. So here are the given quantities. We know that the total energy, like in the last problem, energy is power multiplied by time. But in this case, we're going to use Q times voltage gives you energy. That's from the definition of voltage. Remember, voltage is work over charge. So voltage is work over charge, which means work is charge multiplied by voltage. Work and energy are the same. So energy is charge multiplied by voltage. But charge is current multiplied by time. And so we get that formula. And then we can calculate energy is 1 ampere hour and the voltage is 1.58. So what's interesting is I times T is 1 ampere hour, because there is I, which is the ampere, and time as a special case is in hours. Okay, so that's 1.58. Number 9, a copper wire has a diameter of 9.266 millimeters. Calculate the power loss in a kilometer of such a wire when it carries 100 ampere. Okay, so this is interesting. You know, we get our power via long transmission cables, and longer the cable, more the power wasted in those cables. So here we are asked to find the power wasted in a cable of length 1 kilometer, which is 1000 meters, and the diameter of that cable is given and the current carried is given. And remember, bigger the current, more the loss. So here the current is huge, it's 100 amperes. So definitely the power wasted is going to be big. So to calculate that, first we have to calculate the resistance of the cable. The resistance is given by rho L by A. Rho is the resistivity of copper, which will be given. And then the length is 1000 meter. Area of cross section is pi r squared. Pi times radius squared. So I've taken half of this and changed it to meters. That's why you see the 10 to the negative 3. So once I get the resistance, which is not quite large, you use the formula for power, which is I squared R. So 100 ampere square times 0.255. So we got to put a square there. Oh, 0.255 ohms gives 25.5 watts. That's the power wasted in 1000 meter of the cable. So imagine if it was 10,000 meters, then you get 10 times that power wasted. So the idea is to have less power wasted. Two important ideas: the cable has got to be very thick, number one, and number two, the current through the transmission cables must be as small as possible, which we will see how it is carried out using transformers in a later chapter. Question: how much time is needed for a surgical cauterizer to raise the temperature of 1 gram of tissue from 37 degrees Celsius to 100 degrees Celsius and then boil away 0.5 grams of water if it puts out 2 milliampere at 15 kilovolts? So this is an electrical heating system. First of all, we need to see that it has to do two things. One, it has to raise the temperature of tissue from 37 to 100 degrees Celsius. And second, it has to boil away 0.5 grams of water. So, as you may have studied in College Physics 1, the increase in temperature is given by the formula mass times specific heat times change in temperature. But when you change phase, like water becoming steam, you have to use the formula mass times latent heat. So we got to do both here. That will give us the total quantity of heat. So mc delta T is the heat required to increase the temperature, and mass times the latent heat of vaporization, which is a constant, will give us how much heat is required to vaporize the water into steam. So the mass is given there. Mass 1 gram changed into kilogram. This is the specific heat of the tissue which will be given. And then change in temperature is 63, 100 minus 37, change. And then mass times latent heat will also be given. So once you get those two, you calculate the quantity of heat is 1349 joules. And then we know, like we did so many times before, that energy is power multiplied by time. Quantity of heat is just energy. So Q is energy. Power multiplied by time, and power is current times voltage. And so rearrange that to make T the subject, and you get the answer as 44.95 seconds. This video was done really fast, hoping that it will help you study this chapter. So I hope you look at this, understand this, study this, and do good on the next exam. Thank you.